Okay. So we were here, we had forgotten about Aaronson-Ambainis conjecture, and now we are just going to think about the Fourier completely bounded version of Aaronson-Ambainis conjecture. And now what I have promised you is that I will introduce what is the Fourier completely bounded norm. And to do that, I have to introduce a few definitions. So we are going to pick vectors of n plus 1 that take values in n plus 1 and have length 2D. And we're going to define an equivalence relation in this space of vectors. And we're going to say that two of these are equivalent if when you take a Boolean string of n variables and then you have an extra variable that is always set to 1. And if you take the products of this x indicated by the entries of I and entries of j, then you have that these products are the same. So, okay, so I and j are equivalent if these products are the same for every element of this kind. So, okay, so maybe this is not very clear and it's a bit of a technical definition. So I'm going to give an example. So let's say that we have m equals 7 and d equal 2. So for example, under this definition we have that these two guys are equivalent because if you take the product of x1, x7, and x6 of any string, Boolean string like this, then that equals the product of x7, x6, x1, and x1. Okay, that is clear because somehow the order here in this product does not change the value of the product. So somehow permuting the entries of one of these vectors gives you another vector that is equivalent under this relation. But there is also other kind of vectors that are equivalent to this that are not obtained by a permutation. So you can think of, instead of putting 2 1s, you can put 2 3s. And these two are equivalent because, again, if you have 2 3s, those are going to square to 1, and you are just going to be left with x7, x6, and the same here. So somehow this is saying that two vectors are equivalent if and only if when you look at the elements from 1 to the n and you count how many times those elements occur in the vector, the parity is the same. Okay? So this only cares about the parity of the occurrences of the elements from 1 to the n of this. Here we have an extra variable that is always 1, the n plus 1 variable, and we kind of need it. We are going to see why in a few moments, but somehow this is the relation that we need. And with this relation, we can define when some matrices behave like Boolean strings. And that is what we are going to do now. So let me consider some dimension, like natural dimension. And let me pick two vectors that are of L2 normal plus 1 of this dimension. And let me pick also matrices that have operator normal plus 1 of this dimension. And by operator norm, I mean that when you look at the matrix as a linear map from L2 to L2, it carries vectors that are of norm at most 1 to vectors of norm at most 1. And we're going to say that U, V, and these matrices are going to have Boolean behavior of degree 2D if they satisfy that when you evaluate the product of the matrices and take with respect to these vectors for 2ij's that are equivalent according to this relation, then these products are going to be the same. So somehow this is saying that the products of these matrices with respect to these vectors behave like if they were products of Boolean strings. So this gives us a notion of Boolean behavior for matrices. Okay?
So the quantifiers actually, this is for all UV?
For all UV. Right? For all. No, sorry. That is
UV fixed?
You fix U, B, and A. And the A's. Like fixing U, B, and A's.
But if U is 0, then it's not, okay, it doesn't really say anything, but okay.
Sure, if U is 0, it automatically satisfies this.
Okay. But you mean this definition depends on UV?
So given U, given B, and given some A's, that tuple of vectors and matrices have Boolean behavior if they satisfy this. In that case, it's trivial, like everything is zero, so it's fine. So somehow this is saying that with respect to some vectors, these matrices behave like Boolean strings, but you fix the vectors. Okay? So this gives a notion of behaving like Boolean strings for matrices. Okay?
Why we need this extra n+1, which is always 1?
So yeah, that is somehow that comes from the structure of quantum algorithm, but I can also give a kind of motivation now, which I'm going to give now. So in particular, given a subset of the numbers from 1 to the n that has size of 1 at most 2d, we are going to find an equivalence class of this set with respect to that equivalence relation that is going to be corresponding to S by this. So we are going to say that all the elements of on this equivalence class are those where the elements that occur an odd number of times here correspond to the elements of S. And for every S, there is at least one element here that belongs to this equivalence class. So that is somehow also why we need this extra variable. So let's go back to the example here. So n is 7, d is 2, and let's say that S is 1 to 3. So what we're going to say is that for every of these vectors, we're going to assign a set from of the numbers from 1 to the n, where that set is the set of elements that appear an odd number of times in this vector. So if we want that for this vector we have one of these elements, we necessarily need some extra variable, because of course a vector that is assigned to S must have 1, 2, and 3, right? But you need something of length 4 because D is 2. So you have to add another variable. And if you want to add another variable that is 1, 2, or 3, then you would get that some of these would cancel, and that would not work. If you want to add another variable that is one of the variables from 1 to 7 that is not one of these, then that would not cancel, but that would add another element to our set. So you need a dummy variable somehow. So that is somehow how you can justify mathematically why we add this, but this also has some motivation from the structure of quantum query algorithms that they have hidden. Maybe for those of you that are familiar with quantum query complexity, this variable comes from the fact that I have lied. So the queries that I have told you that a quantum algorithm makes is not exactly what a quantum algorithm does. They do a controlled version of those queries. And somehow this control is going to put ones in some part of the diagonal of our Oracle OX unitary map. And those ones are going to correspond to this extra variable that is always set to 1. So coming back to here, the only way that I can get that this vector is assigned to this other to this set is just adding the dummy variable, what is 8, because I had 7 variables, so the extra variable, the dummy variable, is the 7 plus 1 variable, so it's 8. And what I have is that if I look at the elements that occur an odd number of times here, then I get that those elements are S. So for every S, this equivalence class is not empty, and also for if two vectors correspond to the same set S, then they are equivalent, is an if and only if. So this equivalence relation is also useful because it allows us to define the evaluation of the characters on these matrices that have Boolean behavior. So if I want to define the evaluation of the character S on these matrices, which I denote this way, what I'm going to do is pick and representative of this class and just take the product indicated by this representative, and this is going to be a good definition because for any representative of this class, this product is going to be the same, thanks to the fact that we are looking at UBs and A's with volume behavior. Okay?
So can you expand a bit? Like, what is this IS bracket inside bracket?
IS bracket. Yeah, okay. So IS, So I'm going to say that for every S, I'm going to take the equivalence classes of this quotient, and for every of these equivalence classes, I'm going to assign a label S that is a subset of the numbers from 1 to the n that has size at most 2D.
But that equivalent class is independent of S, right?
Like what I claim is that for every equivalence class, and every element of the equivalence class, when I take the elements that occur an odd number of times, they are going to be the same. So that set of elements that occur an odd number of times are going to be my set S.
Like what's like IS inside bracket? So IS is a vector or is a number?
It's a vector.
So what does it mean to put it inside bracket?
Oh, that is usually the way that I think that is the notation I use. Maybe it's not that standard to talk about the equivalence class. So this is the equivalence class of some vectors, and these are representative of the class.
So is I to the S different than I? Like what is I to the S?
Okay, maybe this is confusing. So
I thought it is.
okay, so like maybe let's go back here. So here, if I have all these guys, then the corresponding S, can anyone tell me what is the corresponding S?
7, 6.
That's it.
Yes.
Okay, so what I'm going to do, like, is label all the, so for every of the vectors that is equivalent to one of these, and thus to every of these.
So you mean that these guys are all in the same class, right?
Yes. So for every element of the class of vectors here, we're going to have that the corresponding set is this.
So in other words, for every I, you will take out the indices that appear all times, and this will form the set S. And then you use this set S to indicate all these I's that like share the same S.
Yes. So somehow, yeah. So and then I pick one of these i's, and that is the representative of the class.
So but this notation, if I just write just alone I to the S, does that have meaning?
Is any representative of this class.
Okay, so in the very, very bottom line where we have A of I to the S,
Yeah, it's understood.
it's all the same because of Boolean behavior?
That's it. Like I pick any representative of the class and the definition is correct. It does not depend on the representative because we are looking only at matrices that have Boolean behavior.
I see, okay. Yeah, it might have been easier, at least for me, to understand this definition if I define a map from tuples to sets that just deletes all evenly occurring entries in the tuple, and then equivalence classes are the pre-image.
Yeah, it's clear that there is something with the presentation here.
This is
But I
great.
hope that now is clear after
Thank
the
you.
conversation.
But it should show that Boolean behavior for matrices is pretty rare, right?
Yeah, like it's difficult to find. That is one of the problems here, that, okay, this norm that we're going to introduce in the next slide, okay, it's bigger than the infinity norm, so in principle it should be easier to work with it, but we don't really know examples. Like we know some examples because we can prove some cases of Aaronson-Ambainis conjecture, but we don't really know in general how to even find matrices with Boolean behavior.
I still have a question. So in the Boolean case, in the top, you can indeed reduce those even numbers because they square to 1. But in this matrix definition, you don't assume they square to identity, right?
No, so you only assume the relations with respect to the vectors.
So why that final line is equal?
This one.
Oh, that product is not just product.
It's not product of matrices, it's product with respect to the vectors.
Oh,
But I guess is it the case that if I just like
oh, I see.
if I look at the Boolean behavior and I just do that for like just a single pair, like 1, 1 and nothing else, and I assume that it's Boolean behavior, does that mean you get?
Yeah.
Does that show that that matrix squares to the identity?
I think that depends on UV. If
It
UV
depends.
is 0,
Yeah,
then,
yeah,
then you like A's can be everything.
Yeah. It's with respect to some vectors. It's like not
For fixed U.
like the U and V's are fixed.
I see. Oh, they're fixed. Oh, okay.
Yeah. So it's not like the matrices have Boolean behavior, but it's the matrices and the vectors.
Sorry, can you explain again why you have this actual dimension of 1?
So, like, are you familiar with quantum computing?
No.
No. Okay, then again, let's say that. So, I want to be able to evaluate all characters, right, of degree at most 3. So, in particular, what I need to be able to do is to, for every character, find a vector that corresponds to the character. Okay. So let's say that we go back to the example that we had before. That is d equal to 2, n equal to 7, and we want to find a vector that corresponds to 1, 2, 3. So that vector is of length 4. And must contain 1, 2, and 3, right? So now, try to complete that vector with one variable in order to assign it to S. So what happens if you put 1, 2, or 3? That would be a problem because then 1, 2, or 3 would cancel and you would only get 2 of the 3.
Okay.
And if you have one of the other variables, like 4, 5, 6, or 7, then you will add another variable and you will no longer correspond to S but to one more. So you need a dummy variable.
I see.
Okay? And with this, I can define an evaluation of the characters on these matrices that behave like Boolean for every character of degree at most 2D. Okay? So now we can define what is the Fourier completely bounded 2D norm. So let me recall that the infinity norm is the supremum of the evaluation of the polynomial on Boolean strings. You can write that as the evaluation of the Fourier expansion. And now you can, instead of evaluate the polynomial on Boolean strings, you can evaluate the polynomial on matrices that behave like, matrices and vectors that behave like Boolean strings of degree at most 2D. And then you get the Fourier completely bounded 2D norm. So here is 2D because this is the kind of behavior that the matrices have. So like if you change the length of this behavior, you might get different norms. Indeed you do. This is a bit technical, but this is the norm that we care about to prove Aaronson-Ambainis conjecture.
Just to be sure, that product of S is not product of S things. It's product of 2D things.
Yes.
Okay.
It's product of 2D things that correspond to S. Yeah. This notation, like it's
No, it's
All of
not.
them give the same product.
Yeah, but I'm just saying it's not going to, for example, S is like 1,
No.
2. It's not just producting A1 and A3.
Yeah.
Yeah, you can identify that. Yeah.
well, this is notation. Yes.
Completely. Then
Yeah.
Yeah.
Okay, so do we understand the definition of the Fourier completely bounded norm?
It's very interesting how you can estimate that if you don't even know like your domain, because there are many. But all of that, you say it's very hard to find, right?
Yeah, it's very hard, but I have an example where I can say something. Like, it's very hard in general, but in some case that I'm going to talk about now, I can. So, like in the general case, that is my problem, that I don't even know how to find relevant matrices that have this behavior. But in a particular case, that is, I would argue not that particular compared to the other cases that we know Aaronson-Ambainis conjecture to hold, then we can say something.
For the definition of the completely Fourier bounded norm, is that the supremum is over the just the vectors or the matrices or what is the supremum?
Of U, B's, and A,
Over all three.
over like these tuples of vectors and matrices that have Boolean behavior. Okay?
Also, why is it called Fourier completely bounded?
So, so somehow when you evaluate things that are defined on some space on some scalars on matrices, that is usually called completely bounded.
Okay.
And this Fourier completely bounded because like has a Fourier flavor, it's defined via the Fourier expansion. That is how I evaluate the polynomial on matrices, via defining an evaluation of the polynomial on Fourier characters. I define the evaluation of the Fourier characters, and then I define the evaluation of the polynomial. But that is my notation. I came up with this, like you can call it however you want.
Do I understand it correctly that this Boolean behavior in particular means that your matrices on these two vectors, you can just commute them?
Yes, you can commute them. You substitute two matrices that like
Same.
the same. Yeah,
Same.
you can.
In any place.
Yes, but for this, with respect to these vectors. So okay, so now let me try to prove the Aaronson-Ambainis conjecture for these Fourier completely bounded polynomials that for a restricted class, which are going to be polynomials P that are homogeneous and the Fourier completely bounded norm, the Fourier completely bounded D norm is going to be at most 1, okay? So here instead of writing 2D, I write D, but I guess that no one is bothered by that. Okay. So what we are going to do, we have this upper bound that is promised by the polynomial method defined, the refined version. And what we are going to do is to give a lower bound for this Fourier completely bounded norm, and we are going to compare it with this upper bound, and we're going to be able to say something meaningful about the influences. Okay? So what we are going to do is to define some explicit matrices where we can, that are going to have Boolean behavior, where we can evaluate the supremum of this Fourier completely bounded norm and get a meaningful lower bound. So first of all, I have to define some dimension, and what I'm going to do is, I'm not going to specifically talk about the dimension, but I'm going to talk about an orthonormal basis of the real space where we are going to work with. So this real space is going to have this orthonormal basis. So now you're going to look at some Rn, and this Rn is going to be of dimension equal to the number of symbols that we have here. So these are just symbols to denote an orthonormal basis of my space. Okay, and these symbols are going to be convenient for us. So here we have a special vector, a vector that corresponds to the empty set, and a vector that corresponds to every set of n of the numbers from 1 to the n that has size smaller or equal than d minus 1. Okay?
What's the first symbol?
It's u.
What's U?
Another vector. It's just a symbol. Like you should take this as symbols that denote the elements of the canonical basis of this Rn. Okay, this is just notation. Like I pick Rm, I look at the elements of the canonical basis, and I use these labels to talk about them.
What is M?
M, okay, I'm not
And
specific.
choose the sum of n.
So these are orthogonal.
Like M
Set of inputs.
would be something like this.
Okay. Okay.
Yeah, so these are the sets of size d minus 1, the size of d minus 2, and so on. Like I didn't want to write them because it's not important. I can choose.
Yeah, but implicit here is that U is orthogonal from the rest, right? So these are.
Everything is orthogonal from the rest. Yes.
What is E? E or is E empty set?
Empty set.
Okay.
This is going to be thought as the one that corresponds to the empty set. Yeah, I mean, I could have also, okay, I want to give like kind of a special importance to this one, but I could just have written this. That is true. Okay. Good. Okay, yeah, okay, now I want to call this V, so it's not very important. But
No.
now nothing works. Now there is no questions, yeah. So we define the matrices like this. We're going to say that when they act on V, so when they act on V, they are going to send, AI is going to send V to the superposition of all these vectors where the coefficient, well, these vectors corresponds to the sets of size S that contain I, but you take the I out of the vector and you don't take it out of the coefficient. And you put a normalization here that is going to ensure that these are contractions, as we're going to see. And after that, somehow we define when you act on some ES, AI like a destruction operator. So somehow what AI is going to do is to check if I is in S. If it is in S, it's going to send it to there's another vector that corresponds to the set where you take I out. Otherwise, it's going to kill it. So this is kind of a destruction operator. Maybe if you come like from physics, I don't know if anyone comes from physics here, but this is what physicists might want to call destruction operator. And somehow this is the way that I'm going to define IS for the non-dummy variables and for the dummy variables.
So for
empty set.
yeah, what's the operator for empty set?
Okay, yeah, for empty set, okay. For empty set, I'm just going to, okay, this is a bit of abuse notation, but like somehow for empty set, like if you have empty set here, then I cannot belong to S, and then it's just going to kill it.
Okay.
So, AI for empty set. Okay. So this is the definition, and what I claim is the following. That E empty set B So I claim that these two special vectors with respect to these matrices have Boolean behavior, okay, of degree D. And I also claim that when you take, now this, before this was like, this like the vector. I'm going to use this vec notation here because I cannot write like a computer. And this expression is going to be very nice, and the expression maybe you can already guess that is going to be equal to this. Okay, so
What is S? Oh, I to the S.
I to the x, yeah.
So that's I star.
No. Yeah, it's more, sorry. Okay, so I have this. So now let me first say that if I prove those two things, then I get what I want. Okay, so first assume that we have proven 1 and 2. Then what we can do is, okay, our P was bounded in the Fourier completely bounded norm. And now, if we believe 1, this Fourier completely bounded norm is bigger or equal than the evaluation of P on this tuple with Boolean behavior. This okay, if we believe this way.
So is that U or EMT? That should be EMT, right?
EMT, yeah. Thanks. So is it empty? So we get this, and if we just apply 2, if we believe 2, then we get this, right? And this is a homogeneous polynomial, so the sum of the squares of the polynomial of the Fourier coefficients is the variance.
It's maybe square, not square root. It's already squared. Does it? Oh, no.
Okay. Yeah, the square root is on the denominator. And then what we got is that 1 is bigger or equal than this quotient. So if you rearrange and take squares, what you get is that the maximum influence is bigger or equal than the variance squared. And this is Aaronson-Ambainis.
And there is no dependence on D.
There is no dependence on D for this case.
So there is no D?
Not in this case. Like but it's very restricted case. Like in a general case, you could afford some dependence on D, but in this case, you don't.
In general, you mean general polynomial.
General polynomials, yes. Yeah. Yeah, this like might look surprising, but I think that is not the. I mean, it's very restricted case. This one.
So should I think about it as D grows, then this constraint that the FCD norm is less than 1, it just becomes more and more aggressive? Like what's
Yes.
compensating for
Yes,
that?
so that is correct. So somehow increasing D in this Fourier completely bounded norm implies, in a quantum computing sense, increasing the number of queries.
Right?
So the more queries that you have, the closer you should be to compute your function. So the smaller should be your Fourier completely bounded norm. So the most powerful this restriction of being Fourier completely bounded on the D norm comes. So yeah, that is correct. Yeah, it's like surprising that you don't have dependence on D, but somehow. So I told you that there was a result by Nikhil Bansal, Macran-Sina, and Ronald de Wolf that was similar to this, like it's not comparable, but was about completely bounded block multilinear polynomials. And in that case, they don't have that in the original version, but for the homogeneous case of that case, they also can get a Aaronson-Ambainis conjecture without dependence on D, but for the homogeneous case. Like, that does not mean like that is going to be true in general. Like, for example, if you want to compare the infinity norm of a polynomial and the infinity norm of its degree D level or degree T level, then here you have quite a discrepancy. It can be even exponential. So I'm not surprised by this because somehow the homogeneous case should not imply, like no dependence on the homogeneous case should not imply at all no dependence on D in the general case.
But do you mean that that's the only obstacle? That
No, there is many
homogeneous
obstacles.
is everything is fine, but
No, like there is many obstacles, I think, like if you want to generalize these things, but that is one particular thing that makes me like not surprised about this one. Okay, so now the only thing that is left to do is to prove 1 and 2. Okay, so let's prove 1. Okay. So we are going to pick a vector is. We are going to write it as is1, isd, and let's see what happens when you apply these matrices to V.
Don't you need to verify the operator norm first?
Like you can review the order, right?
No, I mean the operator norm of A, because you want it to be at most 1, right?
Sure, but like you can first check the algebraic conditions that you need to satisfy, and then check that they are contractions, or vice versa. Like, that's not
you
really
will
hard.
check it.
I will check it, yeah. Like having Boolean behavior implies that you have to check both, that they are normalized and that they satisfy the algebraic conditions given by the Boolean behavior. So, okay, so first apply this. Okay, look, okay, we might want to divide this in cases. So the case where the size of the set is D, then what we have is that the only possible IS is going to be, so if the size of the set is D, then ds is going to be just the numbers, different numbers, and the only possible is going to be and permutations, right? So the only possible is going to be the one that is given by the elements of S and the permutations, because somehow you need all the elements of S to appear on IS, and as the length of IS equals the size of S, that is the only possibility. Okay, so we are going to begin with this case. Let's say that, so, and for simplicity, we are just going to assume that IS is this one. Like maybe you can permute, but it's easy to check that these don't not really care about the permutations of the IS. So first we are going to apply, to see what happens when you apply AID here. So what happens? So we go to this definition, and what we're going to do is to send B to okay, And then what is going to happen when we apply the second matrix? Then we are going to kill all these guys that do not contain ID minus 1. Okay? So we have the same thing, but now we require these S primes. Oh, sorry. Yeah. We require these S primes to contain both ID and ID minus 1, right? And you can see how it goes. So at the end, after the applications, there is only one that is going to survive, which is the S prime that contains all the I1 to ID. So the only one that does that is ES. And the vector corresponding to the last step is going to be E empty set. So you get that, okay? So in particular, so you can somehow see that this does not really care of the order of the i's, right? Like if you had another permutation, that does not really matter because at the end you will have killed everything that does not contain the elements of S, but at the end you would end up with S anyways. So this proves that for this case we have Boolean, like we have the algebraic part of Boolean behavior, okay? And we end up with this. So in particular, we also have proven 2, because now if you take the product of B, apply all the matrices, and then take the product with respect to E empty set, then you get this. Okay, so we have also proven 2 for this kind of vectors. And now what this remains to do is to check cases of other S and check that everything is normalized. Okay, so now say that S is smaller or equal than, of size smaller or equal than D, smaller than D, sorry. And then there is a few i's that correspond to S. Some of these i's, what they are going to have is that this is kind of abuse of notation, but they are going to have n plus 1. Sorry, they are going to have n plus 1 inside the I. So maybe some of these i's have some entry that equals n plus 1. And in that case, what we are going to have is that you so this is going to be 0, because if you have n plus 1 at some point, then you're going to multiply by the zero matrix, so that is going to be 0. And if you don't have n plus 1, what is going to happen? Given that this S has size smaller than D, you're going to have a repetition, at least one repetition of one variable. And what is going to happen is that you will kill twice the same vector, the same variable, and that is going to result in 0. Okay? So somehow, yeah, I won't write it, but this case is also checked. Okay? So these matrices have the algebraic part of Boolean behavior, and they are also normalized. So matrices and vectors, the matrices and vectors have the algebraic part of Boolean behavior, and what is left to check is the normalization. So these vectors are normalized because they come from the canonical basis, okay? So the vectors have norm at most 1. And now what is left to do is to check what is the norm of the matrices. And this is also kind of simple because, of course, this is contraction because it's just a 0. And now the other matrices, notice something, that they are going to take the vectors of a orthonormal basis to orthonormal vectors. Like that is simple to check because somehow they are carrying vectors, like you can see like somehow levels of the vectors, put them in levels according to what is the size of the set of numbers from 1 to the n that they correspond to, and they are going to carry vectors of different levels to vectors of different levels. So these matrices AIs carry an orthonormal basis to orthogonal vectors. So what is left to do is to check that for every vector of the basis, the matrix maps it to a normalized vector. And of course, for these vectors, this is clear. They are just being taken either to 0 or to another basis vector. And the only one that we have to check is the first one. And to check the first one, we just have to compute this and see that it's smaller than 1. So what we have to do is to compute this. Okay, this is an orthonormal basis. Oh, sorry, I forgot about this. This is an orthonormal basis, right? So the 2 norm of this is just the sum of the squares of this divided by this square, like the 2 norm square. Okay, and this is just the influence of the ith variable, right? And this by definition is at most 1.
Just to be clear, this like V, like AI mapping from, I mean, AIV is not also orthogonal to AIES, right?
AI.
AIES versus AIES prime are orthogonal, but it's not orthogonal to AIV.
It is.
It's not, but it's sort of practically orthogonal, so you...
Yeah, it's practically orthogonal. It's okay. I'm just saying it's not
Like
orthogonal.
AIV is
So
also
maybe if divide by 2 the first formula, it will be okay.
Yes,
So
it
there
will be
just a
okay.
constant or
Just
something
to
like
make sure that it's
Doesn't-
not
doesn't
completely
matter.
orthogonal.
It's orthogonal. Like AIV is sending everything to sets, like to vectors labeled by sets of size d minus 1.
that.
Yeah, but for
Formula you are
AIES,
right,
it's-
but it doesn't matter.
But for AIES, you send it to a vector of corresponding to a set of sizes at least one smaller, right?
yeah, it's so their inner product could be like this: p hat s over square root max in.
They meet.
They are not
They
also-
little bit.
No, but like AIV is orthogonal to AIES. That is what you want.
Why it's orthogonal?
Like, the important part is that
Smaller.
Oh, okay, this is true. Yes.
and that is what you need, right? You need like that the vectors of this orthonormal basis are carried to orthogonal.
Oh, that's d
vectors.
minus
Oh,
1.
it's
It's
d
d
minus
minus 1.
Yeah, you yeah.
Okay.
You can also call, maybe you could.
But actually, even if it would be what's it called a D, it would still work. Okay.
Okay, so if I can carry on, like I have one last slide. So now, we have proved this case of the Fourier complete model Aaronson-Ambainis conjecture, and the question is, what is next? So somehow, I think that there is a few things to try in order to make some progress on Aaronson-Ambainis conjecture, maybe not proving in full generality, but if you want to extend this method to other Fourier completely bounded polynomials that are not necessarily homogeneous, what you really need is...
I didn't understand where you used homogeneity.
Yeah. So what we have to be careful is that with this definition, so yeah, here. Okay. Here, what happens if you take a set of sizes smaller than D, everything becomes zero. And I don't know how to, so for homogeneous polynomials, that is not a problem. Okay? Because for homogeneous polynomials, that is the value of the coefficient. But for non-homogeneous polynomials, you might be missing some coefficients.
For non-homogeneous, you get the estimate, but it's not the estimate you want. It's weaker than you want. It's weaker than you want.
Yeah, you would not get the variance, you would
Like just kill.
you would get the variance of the degree detail. But that
It's a variance only of the top thing.
yeah. Okay. And also, like, yeah, some things like this homogeneous of degree D with respect to the degree D Fourier norm. So, like, you can also look at polynomials of degree D with respect to the Fourier completely bounded D prime norm. And that should be the case that you should care about. So, yeah. But like, in general, what we need in order to extend this is new ways of lower bounded the Fourier completely bounded norm. So this comes back to your question, what are matrices that satisfy that they have Boolean behavior? Okay, I gave you some matrices that are somehow useful for this particular case, but they don't really say much about a general case because of what we have just pointed out. And it would be nice to have similar matrices that would have similar relations, like that they would satisfy something like this for general polynomials. And maybe you can even afford to have some dependence on the degree. You don't even need to satisfy that. And it would be nice thus to find new ways of lower bounding the Fourier completely bounded norm. So maybe that is a way to go. I don't know how to do that. Like I have asked people of different fields that I think that they are related to, that are a bit related to this Fourier completely bounded norm, and no one really gives me a point where I can begin to read and get familiar with anything that might lead to new ways of lower bounding this norm. But maybe there is, maybe some of you know. That is one way to go, and maybe also other ways to go that are not directly via this approach are looking at this case. So this case, we go back to multilinear forms where we have the variables divided into blocks, and in every monomial of the support of the polynomial there is one and only one variable of every block. So is linear with respect to every block. Sorry for repeating, but I just want to make sure that everyone understands. And here, we saw that Monteraro, if these coefficients are plus minus 1, he already proved Aaronson-Ambainis conjecture, but that is kind of narrow. And it would be nice if you have general multilinear forms that are bounded on the infinity norm to prove it. So here, if you, instead of putting minus ones and ones, you put matrices that are bounded, then we know that the Aaronson-Ambainis conjecture holds. That is essentially what the work of Van Salzin and the work proved. Okay, but we don't know what happens if the infinity norm is the only guarantee that we have. And this was already asked by Montanaro and by Aaronson and Ambainis. But so this somehow feels like the first natural step to do before proving the general case, but still it has been asked and it has been open for 15 years. So this might not be that easy, but still would be interesting for the Aaronson-Ambainis conjecture. And maybe another way to go is, okay, what happens with this Fourier completely bounded norm is that in principle it's simpler to prove the Aaronson-Ambainis conjecture because you have more structure, but it's also very difficult to work with. Like, we don't even have ways of evaluating the supremum apart from this one. So we don't know even matrices that behave like Boolean strings. But we can also do something in between. So something in between would be to, instead of looking at the Fourier completely bounded norm, we could look at the infinity norm, but now when evaluating on complex scalars, and let's see what happens. And if we prove this conjecture where we change the infinity norm by the infinity norm in the complex space, then we would also.
What does it mean with this norm? Is it like on the disk or polydisk or what?
Yes.
It's polydisk.
Missing polydisk. So this conjecture might be easier because, of course, if you evaluate the polynomial on complex bounded numbers, you can in particular evaluate it in real bounded numbers. So this restriction is stronger than just having that the usual infinity norm is at most 1. And this is still relevant. So quantum Fourier algorithms output polynomials that have this property that they are bounded like this. So maybe this is something in between the usual approach and the Fourier completely bounded approach that is more tractable because we have tools. I don't know, I have asked a few of you if you have tools like to attack this. It's not super clear how to, but in principle can be a way to go. And yeah, so this is, I think, some nice open questions that would give some understanding of how to prove Aaronson-Ambainis conjecture, and that's all I want to say. Thanks a lot.